Welcome to the lecture of Renewable Energy System. In today's lecture, we will discuss about the hydropower turbines, type and their characteristics. Hydro turbines can be grouped according to the head that they use to harvest hydropower and their mode of operation. A rough classification according to the available head appears below. The turbine appropriate for low head has the head height less than 10 meter. The turbines appropriate for medium head, which has the height of between 50 meters to 10 meters, and turbines appropriate for high head, those turbines who have the head height above 100 meter. Another common classification of hydroturbines is based on their principle of operation, such as impulse and reaction type, that describes how the turbine transforms potential and water energy into rotational mechanical energy. The rotor of the reaction turbine is fully immersed in water and is enclosed in a pressure casing. The runner blades are profiled so that pressure difference across them impose lift forces just as on aircraft wing, which cause the runner to rotate. Two main type of reaction turbines are the propeller with Kalpan variant and Francis turbines. In contrast, an impulse turbine runner operates in air, driven by a jet of water. Three main types of impulse turbines are in use: the Pelton, the Turgo, and the cross-flow. Turbine choice is based on the principal site characteristics, that is available head and flow including flow variation, that is if the turbine operates in part load condition. For example, when available discharge throughout the year is typically lower than the turbine design discharge. The approximate range of head flows and power applicable to each turbine types are summarized in this diagram. It shows the range of head, flow rate, and corresponding power which best suit each other. These depend on the precise design of each manufacturer. According to the diagram, when the flow rate of water is low and the head height is high, then Pelton and turbo turbines are used, that is the area highlighted by the purple color. On the other hand, when flow rate of water is high and the head height is low, then propeller-based turbine, that is Kaplan turbines, are suitable, that is the area highlighted by the blue color. And in between these two ranges, Francis turbines are used, that is the area presented by the pink color. Note that effective head is not the only factor determining the most appropriate type for a given situation. The available power also matters. It should be noted, however, that the boundaries are by no means clear cut, such as these boundaries, and other technical issues are or criteria such as cost, simplicity in manufacturing, or ease of maintenance can lead to choice outside these range. The small scale installation can also be classified by the available head and flow rate, but the ranges may be very different from those of large plant. Many of these plants are run-of-river, with head of only a few meters, and as little as 10 meter could be regarded as high head for a very small plant. The corresponding choice of turbine type may vary appreciably from those indicated in this diagram. Typically, impulse turbines are most efficient for high head. The Pelton turbine is the most widely used impulse turbine. It comprises a runner with blade shaped like a double spoon and one or more nozzle, such as shown in this diagram. So this is the nozzle and that is the runner that convert the kinetic energy stored in this water flow into rotational mechanical energy. The jet from the nozzle hit the runner blade and transform the flow kinetic energy into rotational mechanical energy. Each nozzle has a movable needle to control its discharge. For a horizontal shaft turbine, the maximum number of nozzles is 2. For a vertical shaft, the maximum is 6. Each nozzle has a deflector, which is triggered when a load rejection occurs. It deflects the eject to control overpressure in the penstock and prevent runner overspeed. Pelton turbines operate in area as shown in this diagram. So here we can control the flow of water that is ejected on the wheel. For a head above 200 meter or lower for small scale system, the Pelton wheel is the preferred turbine. It is essentially a wheel with a set of double cups or buckets mounted around the rim, such as shown in this diagram. A high-speed jet of water formed under the pressure of the high head hits the splitting edge between each pair of cups in turn as the wheel spins. So the water ejected at this point on this line. Also, the turbo turbine is based on the Pelton turbine. The turbo differ only in the angle at which the jet strikes the runner plane, which is about 20 degrees. Therefore, water can enter at one side of the runner and exit on the other side. So the flow rate is not limited by the discharge fluid interfacing interfering with the incoming jet as in Pelton turbine. Consequently, the runner of a turbo turbine can have a smaller diameter than a Pelton to produce equivalent power. Turbo turbine ability to handle a large volume of water than a Pelton wheel of the same diameter gives it an advantage over the power generation at medium head. The cross-flow turbine has a drum-like rotor with the solid disc at each end and gutter-shaped slat adjoining the two discs. Water flows transversely through the turbine, entering at the edge and emerging on the opposite side, thereby generating additional energy. The water passes around the curved bowl and under optimum condition give up almost all its kinetic energy, such as shown over here. The power can be varied by adjusting the jet size to change the volume flow rate or by deflecting the entire jet away from the wheel. The number of jets depend on the prevailing flow rate. This means the prevailing flow rate determines the required number of jets. In practice, one jet can handle a flow rate of 10 meter cube per second in maximum. However, for a Pelton turbine should be given the required number of jets to ensure the flow rate. The efficiency of a Pelton wheel is greatest when the speed of the cup is half the speed of the water jet. As the cup speed depend on the rate of rotation and the wheel diameter, and the water speed depend on the head, there is an optimum relationship between these three factors. The main advantages of impulse turbines are: number one, easily adapted to fluctuating discharge with almost constant efficiency. avoid penstock overpressure, and easily control runner over speed. Comparatively easy to maintain. Reaction turbines use the water flow to generate hydrodynamics lift forces that propel the runner blades. Reaction turbines have a runner that always function within a completely water-filled casing. Reaction turbines have a diffuser known as a draft tube below the runner through which the water discharge. So over here, the draft tube deaccelerate the water discharging and reduce static pressure below the runner, thereby increasing effective head. The propeller turbines, as shown in this diagram, is an axial flow turbine with a propeller-like runner and 3 to 6 runner blades depending on the design head. The runner operates like a reverse boat propeller. Various configurations of propeller turbines exist. For efficiency, the water must have some swirl before entering the turbine runner. The runner absorbs the swirl and the water flow that emerges goes straight into the draft tube. Method for adding inlet swirl including using a set of guide vanes mounted upstream to conduct the water spiral into the runner. Another method is to house the runner in a nail shell so water enters tangentially and is forced to spiral into the runner. Adjustable guide vanes can vary the flow admitted to the runner. The Kaplan turbine is the type of propeller turbine with adjustable runner blade as well. The advantage of these turbines is that the angle of the blade can be varied when the power demand changes. These type of axial flow turbines are suitable for very large volume flow and low head height. The mechanical equipment for adjusting turbine blades and guide vanes increases cost but improves efficiency over a wide range of flows. Double regulation of turbines is a feature now widely used for river installation with significant flow variation during an average year. In Kaplan turbine, the optimum blade speed is greater than the water speed as much as twice as fast. This allows a rapid rate of rotation even with relatively low water speed. In case of axial flow, there is no need to feed the water in from the side. It might appear to be better to let it flow in along the axial axis instead of deflecting it through a right angle. But if the water flow in along the axis of the turbine, the generator will get in the way and it will get wet. Another variant of reaction turbine is the bulb turbine. The bulb turbines are named after the shape of the upstream watertight casting in which the generator is enclosed. Typically, bulb turbines are implemented in low-head hydropower scheme with high output. They are used in hydropower plant with head up to 30 meter and offer reduced size and cost compared to vertical Kaplan turbine due to the almost horizontal water passage in the draft tube which requires a smaller evacuation. Similarly, S-turbine provide an economic solution for low-head small hydropower scheme with capacity up to 10 megawatt. The S-turbine offers good accessibility to components, reliability, and a long service lifespan. The Francis turbine is the most common water turbine in use today. Water flows readily into the runner and exits axially into the draft tube. The runner is surrounded by a spiral cases, in which guide vanes are integrated to direct the water tangentially to the runner. The Francis turbine was originally designed as a low-head machine installed in an open chamber without a spiral casing. Although efficient, the Francis turbine was eventually superseded by the propeller turbine, which is more compact and fast runner for the same head and the flow condition. However, since many open flume Francis turbines are still operated, this technology remains relevant for refurbishment scheme. Advantages of reaction turbine are as follow. It requires less installation space, that is, runner are smaller than Pelton turbine. It provides a greater net head and better protection against the downstream high flood level because it can run submerged. It offers greater runner speed. It offers high efficiency for higher power values. Francis turbines are installed for the head height between 15 meter to 600 meter. The optimum blade speed is greater than the water speed, as much as twice as fast. This allows a rapid rate of rotation even with relatively low water speed. In case of axial flow, there is no need to feed the water in from the side. It might appear to be better to let it flow in along the axis instead of deflecting it through a right angle, but if the water flow in along the axis of the turbine, the generator will get in the way and it get wet. Turbine selection should include a comparison of the relative efficiency of turbine type and their operation under all conditions, especially reduced flow. Typical efficiency curves are shown in these diagrams. The Pelton and Kalpan turbines retain very high efficiency when, when running below design flow and operates well under part load condition. Part load is an operation below the full rated load at a given turbine rotational speed. Cross flow and Francis turbine efficiency drops more sharply if they run at below half their normal flow. Hence, they are used in run-of-river plant scheme with constant flow. According to the efficiency shown in this figure, it is practical to determine minimum admissible flow condition as a percentage of the design flow. For Pelton turbine, 10 to 20% of design flow, depending on the number of nozzle, is the minimum admissible flow condition. Similarly, Francis turbine has 40% of design flow, and Kalpan turbine has minimum admissible flow condition about 20 to 40% of design flow, depending on the double regulated or semi-regulated system. If the flow falls below this minimum level, the power plant must shut down to avoid damaging the turbine due to the heavy vibration. Sometimes more than one turbine is installed to prevent turbine shutdown during low flow season, depending on hydrological condition and the hydropower scheme. There are many ongoing research on the turbine improvement. The ongoing research aims to extend operational range, improve reliability, and reduce cost and environmental impact. The main focus is utilizing low head, which is up to 50 meter, or very low up to 5 meter head. Thus, hydropower can be produced at many sites previously considered unsuitable due to the limitation of the conventional technologies. Few of the technologies are mentioned here. The variable speed generation offer advantages essentially based on greater flexibility of turbine operation in situation where the flow or the head deviates substantially from their nominal value. The main advantages related to a considerable reduction of the efficiency variability and reduced turbine scratches. Another new technology is matrix. This technology aimed to develop small identical compact turbine generator units to be inserted in matrix-shaped frame. The number of units in the matrix can be adapted to available flow. During operation, it will be possible to start and stop any number of units. Thus, the unit in operation will always run under optimum flow condition. This technology is well suited to installation at existing structures such as irrigation dam, ship locks, etc., where water is released at low head. A fish-friendly turbine is an emerging technology that provides a safe approach for fish passing through hydraulic turbine, minimizing the risk of injury or death. Rivers often transport large amount of sediment, especially during flood events. If the sediment contains hard minerals such as quartz, guide vanes, runners, and other steel parts are subjected to high scratches, hereby rapidly reducing efficiency. New solutions include coating steel surface with hard wearing ceramic top layers are included in this type of research. The generator transforms mechanical energy into electrical energy using an excitation system. Depending on required runner speed and power station characteristic, the generator types are classified as follow. The horizontal and vertical hydro generator are classified by their axis location. Usually large and medium-sized units adopt a vertical layout. Medium and small capacity units adopt horizontal layouts. Synchronous generators are equipped with the DC electrical or permanent magnet excitation system associated with the voltage regulator that controls output voltage before the generator is connected to the grid. Synchronous generator excitation is independent of the grid, so synchronous generators can produce power even without grid connection. On the other hand, asynchronous generators are unable to regulate voltage output and run at a speed related to system frequency. If isolated from the grid, they cannot produce power because their excitation current comes from the grid. Typical generator efficiency in small hydropower plant installation schemes increases with rated power. For very small unit, for example 10 kilowatt, efficiency can be close to 90%, whereas for larger capacity turbines, that is more than 1 megawatt hydropower plant, the efficiency approaches about 98%. As of generator selection criteria, a low head river run-of-river plants usually use low-speed generators in connection with the bulb or cub plant turbine. High-head hydropower schemes usually require high-speed generators in connection with Francis and Pelton turbines. Variable speed pump storage plants usually use asynchronous motor generators that allow adjustment to the pump turbine rotational speed. Hydraulic steel structures are installed in hydropower plant schemes to control water flow using gates or valves and are classified according to their operational purpose. First purpose is to serve the gates. The service gate for continuous flow regulation in the waterway or of the water level in the reservoir include spillways gates, bottom outlet gates, and lock gates for navigation. Emergency gates are used to shut down water flow in conduct or open channel. Typically, they are designed only to be fully open or fully closed, and they include intake gates, gates upstream of penstock service valves, draft tube gates, and the gates installed upstream of bottom outlet gates. The maintenance gates are used to empty the conduct or or canal for equipment maintenance, that is turbine, pump, or other gates. The most common type is the stop-lock gate. The distributor vanes or turbine needle valves are used for the flow regulation. Trash racks are nearly always required at pressure pipes entrance and intakes to prevent floating debris from entering. Today, the most commonly used gauge types are flap, cylinder, stop log, slide, caterpillar, meter, roller, segment, sector, drum, fixed wheeled, and whizzer. Each gate type is unique in terms of purpose, movement, water passage, leaf composition, location, and skin plate shape. Gate type selection depend on purpose, dimension of the opening to be gated, climate condition, that is passage of ice slab, and option for gate operation. In this lecture, we have talked about the types of hydropower turbine and their characteristics. Further, we have looked into the selection criteria of the turbine according to hydro system. Today lecture end here. Thank you for listening.